Hello, this is Justin Schaper with my final project presentation for ADTA 5550 Fall Semester 2023, Convolutional Neural Networks. As a preliminary, in Part 1, discussion of use of TensorFlow directly in coding. In this project, TensorFlow was exclusively used. Keras was not used in the final project, unlike in earlier assignments. Part 2, data set of images. After some research, I located an image set that seemed to be appropriate for a convolutional neural network type of problem. It's a facial emotion expressions image set available on Kaggle. This consists of a tagged image data set that has 7 different categories of emotions. It's available on Kaggle at the URL listed on the slide. This consists of 48 by 48 grayscale images of faces with tagged emotional expressions. Emotions are one of 7 categories: anger, disgust, fear, happy, sad, surprise, and neutral. These have been pre-divided into a training set with over 28,000 images into a validation set of over 7,000 images. The image you see on the slide there is actually one randomly taken from the data set. Part 3, obtain the Cipher-10 data set. The Cipher-10 dataset was downloaded from the Canvas module to local laptop. The upload was performed using the Google Cloud Console with SSH upload function. And after upload, moving the files over into the appropriate subdirectory in the Jupyter Notebook folder. Part 4, build, train, and test of the convolutional neural network on the Cipher-10 dataset. From a design point of view, the initial approach on this was very similar to the earlier homework assignment. This consisted of 2 paired layers of convolutional neural networks and associated pooling layers. These in turn then went through a flattening process to then feed into a feed-forward fully connected neural network with ReLU activation. That in turn had a dropout layer, which then finally at the end fed into the output layer. Note that although the image here is of a handwritten integer, the images in the Cipher dataset are actually of a variety of objects, including things like trucks and vehicles. These are in the Cipher dataset are color images, not grayscale. So that was another very relevant difference. That also implied that there are 3 channels of input as opposed to 1 channel, which was the previous MNIST exercise. That will become relevant later on as we compare performances from the Cipher and the MNIST models. With the images, although the slide doesn't reflect this, the images again were 32 by 32, not 28 by 28. I didn't edit the slide diagram for that, apologies. But again, the images are 32 by 32 color on 3 channel as opposed to the 28 by 28 grayscale, feeding out to 10 labeled images, though similar to what was done on the MNIST, although in this case, the 10 categories were the type of object of the image as opposed to handwritten integers. The layer 1 pair consisted of a convolutional layer with a convolution shape of 1 by 32 by 32 by 3. Again, the 3 is the number of channels necessary for the color support. That leads to a 2D data size of 32 by 32, again, input shape of 32 by 32 by 3, and a corresponding output shape. The filter or kernel size was initiated at 5 by 5 with stride set to 1. Padding is same. Activation function layer is again ReLU. And then again, the input and output shapes is 32 by 32 by 3. The max pooling layer was set up with a kernel size of 2 by 2, a stride of 2, meaning that the window shape there is a 1 by 2 by 2 by 1. Padding is same on that. Again, 32 inputs, so input shape of 32 by 32 by 3, representing the color input, and then the output shape. This was in turn fed into a layer 2 pair consisting of a convolutional layer and a pooling layer. The convolutional layer on layer 2 here, following the MNIST homework earlier, was now at a 1 by 32 by 32 by 64 input shape. 2D size still 32 by 32, input 16 by 16 by 32, again with a depth of 3 though for the input channel, and then an output channel of 32 by 32 by 64. The kernel was set at 5 by 5 with the filter shape 5 by 5 by 32 by 64, again using a stride of 1, stride shape of 1 by 1 by 1 by 1 with padding the same, activation layer as ReLU, no filter applied there, and the input shape and output shape is stated. The pooling for layer 2, again max pooling, kernel size of 2 by 2, kernel and window shape 1 by 2 by 2 by 1, stride again at 2, stride shape 1 by 2 by 2 by 1, same on padding. Input channels is 64 and output channels also 64. On the feed forward fully connected layer, which is fed from the second convolutional layer and pooling, this was a fully connected layer, 7 by 7 by 64 by 1024 in the output, then a dropout layer at 1024 by 1024, and then finally the output layer at 1024 by 10, and the 10, of course, corresponding to the various object labels associated with the data set. Results of the initial run through after much debugging, the accuracy against the test data set was for the first step at 10.5%, but jumped to 41% by step 100. It plateaued out around step 1000, which was significantly slower, as we'll see on the MNIST set. The final output against the test data set hit an accuracy of around 67 or 68% after 5,000 steps. These results suggest that the CNN is significantly better than a random. Again, a random, we would expect an accuracy out of 10 labels to be around 10%. And so getting to a roughly 2/3% accuracy, 67% is much better than random. But by comparison to the MNIST set is quite a bit lower. Again, this might be a good result, but it's worth thinking, considering what the actual application or use case would be. This could be production worthy depending on the need. As by way of example, in my own work experience in healthcare, models that have a 67% accuracy might be very useful for an operational billing or coding use case, but would probably not be considered production worthy for a clinical use case, especially in the context of clinical decision support. So, for example, a model that makes a prediction about sepsis occurrence in patients being admitted to the emergency department, that's one where we would look for an accuracy rate of 90% or higher. But if we're talking of an accuracy rate of 2/3, that might be really relevant in a billing context, but not for a clinical decision making. Okay, now comparison of the convolutional neural network performance between the Schaper and the MNIST. As described in the report, after running both models, the accuracy data was abstracted out of the Jupyter notebook, put into an Excel spreadsheet, and then aligned based on step count. The graph, as displayed on the screen here, is a comparison of actually the 3 different models, specifically the MNIST model in the bright orange, the original Schaper model, as we just discussed on the design, in gray, and then the subsequent redesign model I've gone ahead and included on this graph. So as we can see from this graph, the MNIST model very quickly jumped after just the first batch of steps to an accuracy north of 90%, plateaued pretty quickly at around 98 to 99%, and leveled off there, very high accuracy rate. By comparison, the Schaper model was much slower to gain accuracy. It got to about 40% after the first 100 steps, but then only got to 50% after the next couple of 100 steps. And so it took much longer to plateau than the MNIST model, eventually reaching an accuracy of around 67%. To go ahead and share a little bit of what the redesign model impact would be, As we'll see in the later slides, I added a third convolutional layer and pooling pair to that, and that resulted in a little bit slower gain on the accuracy, but plateaued out at approximately the same as the original Schaper design. So we'll talk about that again in a couple of slides. As to critical thinking around what the reasons might be between the differences here. First of all, in the Schaper data set, these are photographic images that are much more complex in both features and diversity. As we think about the data set there, we have color images that have true photographic images taken from the real world that are trucks, cars, and other kinds of objects that all come in different shapes and sizes, different lighting, different color palettes. We have real world image artifacts such as shadows and glares that also contribute to the complexity. By comparison, the MNIST handwritten integers, although they are varied, the variation is still relatively minor in detail by comparison. There's just simply a limited number of features to consider. Simply put, there's only so many ways to write the digit 2. And so that, I think, is certainly reflected in the difference, that what the models are trying to accomplish in both cases is considerably different. The type of problem is considerably different. So with MNIST working in grayscale and a very limited set of features, the model is much more likely to hit a higher level of accuracy than in Schaper, where we have much more complexity and diversity in the images used in the training. And then just a probably obvious note, but one worth calling out, is that fundamentally there is a geometrical difference in grayscale and color. In color, although we're only adding 3 channels, that level of complexity is multiplicative. It's not just simply additive. So we're now dealing with basically 3 times the data space or search space as we're working through the variation between the images. So the first pass here, thinking about this, the image complexity is dramatically different in the 2 use cases. And then also color versus grayscale represents another portion of that. So now to the redesign of the convolutional neural network. First pass on this was to simply take the second convolutional and max pooling layer and replicate it. Just double that up and add a third convolutional max pooling layer into the model. Other than accounting for the differences in the connections, everything else was essentially left the same. Again, on this diagram, although not accurately represented, the input is from the Schaper data set, not the MNIST. So having a color input sequence with 3 channels, and then the 32 by 32 image size, unlike is stated here on the slide. But other than that, the architecture and design being the same, the 3 convolutional layer and max pooling pairs then fed through a flattening process into the fully connected feed-forward neural network layers, which in turn included a dropout layer. And then finally, as the output, 10 output neurons representing each of the 10 potential image categories. With the results on the redesign, I was somewhat surprised that there was not a substantial, really a notable improvement. Again, after extensive debugging, the accuracy against the test data set at first step was at 9.8, just under 10%. It did jump to about 35% by step 100, excuse me, and then plateaued around step 1000. But it did continue to slowly improve. At step 1000, it's probably worth calling out. At that point, it was actually still below the 2-layer pairing under the original model design. But by the 5,000 steps, it actually had come to almost identical accuracy results versus the original design. So This suggests that the CNN is significantly better than random, again, as stated before, with 10 different labels. A random allocation, we would expect it to be 10% accurate. We're getting much better than that. We're getting around 67%. But again, whether or not we would want to deploy this in production very much depends on the use case and the cost-benefit analysis, especially when considering inaccurate predictions. So in conclusion, it's clear that convolutional neural networks are incredibly effective at image recognition. Image complexity and diversity greatly impacts the level of effectiveness, though. As we know, not just from the class, but from real-world examples, convolutional neural networks have been used in a variety of use cases, image recognition being one of the foremost of those, along with audio and other types of use cases similar. But it really comes down to that kind of multi-layered representational learning that is current in complex data sets that have that kind of hierarchical patterning. That said, the level of training that has to go into a convolutional neural network and the really trial and error around the layering and the different parameter settings is where the heavy lift is. And it is very much use case specific. One of the routes I went down before realizing I was looking at the wrong set of instructions was trying to build out a CNN around the data set that I initially researched back in the early part of the presentation here. So looking at the Kaggle emotion and facial recognition data set. That data set actually seems like it would be very tractable to a CNN. However, in that effort, I quickly figured out, and plus with some guidance from Dr. Nguyen, that the 48 by 48 image size that had, even though it was grayscale, was causing quite a bit of complexity. It was a very high number of images in that data set. I was running into issues and errors in Python that were likely the result of basically memory overflow errors. And that really brought home for me, just to the extent that the problems of CNNs are very specific and very particular to the use case at hand. So taking a model, for example, that's been trained on the MNIST set and that basic architecture, and just something as simple as adding more dimensionality to the image sets, adding more images with color, for example, or adding more images that have a broader diversity in their categorization or in the underlying variety of the data set, that by itself means that that same architecture that worked great before may no longer work and may require a very different approach in the design and certainly in the training and testing. And again, all of that in mind, thinking about the use case. Again, spending 25 plus years in healthcare analytics and data science work at more of a management level, I cannot emphasize enough how important it is to understand the real world application of the given model that's being considered. There are so many different things that come into effect when looking at that. I described earlier how a clinical decision support tool is very different from one for coding and billing. Relevant to that is the audience that will be receiving the results from that. So for example, if you're writing or deploying a model where the primary consumer of the output of that model will be clinicians, like we've talked about in some of the discussion threads, it's really important to make the right first impression with the clinicians and to make sure they understand what's really going into the black box of that algorithm. I've had firsthand experience of deploying models, predictive models, although in most cases more ML than deep learning, where the explanation of the reason behind the prediction was not entirely clear. And most of the doctors were very resistant to even taking that into account when there was not clear evidence of why something had effectiveness. That was one that they were more likely to just ignore or worse, even argue against, although in most cases just ignoring it would have the negative effect. So understanding the audience, understanding the use case and the potential impact, both the false negatives and false positives. In a clinical setting, a false negative could mean that a really serious impact could result because a patient is not being treated appropriately. We think about the discussion thread again earlier around the diagnostic of diabetic disease related issues. Those impacts are real, and they are real in terms of the real world and in terms of real people. So in that context, a false negative, missing something that is really there, could be really dramatic and have a serious impact for the people involved. On the other hand, having something that is, whether an item gets included in a bill or not, may be relevant, and certainly the dollar value is relevant to the use case and the value proposition of the model, but that has a different kind of impact than certainly clinical care. I think the last point that I would make out of my own experience through this class is just that with convolutional neural networks, the more obvious things that I've thought about in the context of, for example, feed-forward fully connected neural networks, where adding additional neurons, adding layers, adding density usually would result in some improvements, although albeit not always. It's really clear to me that in convolutional neural networks that is not predictable, that as you work through the use case, you work with data, adding or removing a layer does not necessarily have the impact that you might think. I would reflect back on one of the earlier assignments when we first worked with him in IST data. The initial design had 2 layers of pairings and had great accuracy very, very quickly. The next iteration that I did in that assignment was actually to remove a layer, a pairing, and that had negligible impact. That actually very surprised me. I was expecting that by removing that layer, the learning and the accuracy would drop off very quickly at the beginning and not plateau at the same level. But in fact, it was actually pretty close. And then the second iteration of changing the number of steps, moving from 5,000 training steps down to 3,000, still had a negligible impact. But on the other hand, as we've seen with this exercise, adding layers doesn't necessarily mean you're going to get a better result either, which tells me there's a lot more going on there than we would have anticipated. So I think that's it for my presentation, and I'm coming up a little short on time, but I've hoped I've shared a little bit, not just about the project, but also real world experience. Thank you.